Semaphore. Don't use it. Let's see why. Alright, a semaphore is a new type of synchronization primitive. Let me give you a little bit of context here. So far, we studied only two types of thread synchronization primitives. The one is obviously the mutex lock, and the other one being condition variable. So these are the tools available to solve any kinds of thread synchronization problems. The thing is, it is good enough. Mutex lock and condition variable, they are enough to solve all kinds of thread synchronization problems. And that's why we call these as the primitives, because you can build different types of objects out of this mutex lock and condition variable. And now we are going to study different type of synchronization primitives known as semaphore. So why we want to learn about semaphore if we have good enough tools already? And also I started by saying that don't use semaphore. So this needs to be explained a little bit. So the mutex lock and condition variable, they are invented in early 70s. And around 1980s, there were some kind of implementations that's good enough. And the idea of mutex lock and condition variable became mainstream and implemented in many production systems in 90s and 2000 and so on. But the thing is, the semaphore came earlier. It's actually invented in 1960s. So semaphore has more background. Okay, so they thought about how to solve thread synchronization problems in 60s. Not just a thread, but process synchronization. And they invented this object in 1960s, and a lot of theoretical works on synchronization problems, basically developing concurrent algorithms, were done by using this semaphore as base object. So there are already code bases and theoretical works done by using the semaphore as the chosen primitives for thread synchronization. And also, because this came earlier, so arguably there are more operating systems available that supports semaphore. In modern systems, you can find mutex lock and condition variable in their systems these days. But there are some old operating systems, they lack support for this mutex and condition variable, but usually they support this object known as a semaphore. And that's the reason why we want to study the semaphore. And also, I have to say this, in real world, because of the fact that people were taught in university classes the semaphore more often than condition variable and mutex lock. So there are more people that feels more comfortable using semaphore than mutex and condition variable. And don't be surprised that some of your coworkers are more comfortable with using semaphore, or your boss in his 50s demand writing code in semaphore. That could be a situation. So that's the reason why we want to study semaphore. But the thing is, they are theoretically equivalent. Okay, so the problems that can be solved by mutex and condition variable can be solved by semaphore. And you may say, okay, so over here we have two objects, mutex and condition variable, and over here semaphore is just a single object. And doesn't this mean that semaphore is better? The answer is no. Okay, there are a lot of reasons why you want to avoid using semaphore when you're given the choice of these two options. All right, enough with background information. Let's see what semaphore is. Shown here is the class interface of a semaphore. as you can see, only two functions, P and V. Okay, I'll explain these functions later. But let's begin with by saying that the semaphore internally stores an integer value. It should be integer. It's not a string, it's not a pointer, it's not a floating point. It should be an integer. So you can imagine that the implementation of semaphore should have integer count, something like this, as its internal member. Okay. All right. So semaphore stores integer value. Okay. It should be non-negative integer value, and it must be initialized. So semaphore has this constructor with this integer n. So whenever you instantiate semaphore, it is very important to initialize the semaphore with initial integer value. All right, semaphores are like integers, except only operations are P and V. Okay, right here, P and V. And these operations are atomic, just like mutex and condition variable. Okay, all or nothing. So the P atomically waits for value to become positive, then decrements. Right. So it's a multi-step operations. So if you call P and the internal count value is positive, then there's no wait. Decrement the count value by 1 and then just return. But if the count was 0, then it has to wait until somebody increments the count to make the count value positive, and then you can decrement the count value by 1 and then P will return. And what I just described should be atomic. V operation. Semaphore V is the one that increments the value. And also, if waking up should be needed, then V will be awakening waiting thread, waiting on this P operation. So P is the operation that decrements count value, and V is the one that increments the count value. And the count value should never fall below 0. If somebody calls P when the count is 0, then it should wait. All right, so semaphores are useful for unlocked wait, interrupt handler, fork join. But the thing is, you will probably don't want to use semaphore. You want to use condition variable in any real-world setting. So this can be explained better by using an example. Over here, whiteboard area. So this is a timeline. This is a real time. Let's begin with two threads, thread A and thread B. And we have a semaphore here. Let's say we have a semaphore with initial value of 2. Thread A calls P. This results in, initially the count value was 2, and P will take a look at the current count value, and 2 becomes 1. And the P will return immediately because it is positive number. And thread continues. Let's say thread B was executing concurrently with thread A, and let's say at this moment thread B calls P here. And let's imagine thread A actually almost at the same time called P as well. So at this moment, thread A and thread B, they both calls P almost at the same time. And the thing is, because of the fact that P operation is atomic, we know for sure that in this race between A and B, we are able to declare a winner. So whoever wins, the P operation will be completed as a whole without the disturbance from the other thread. Okay, so let's say in this particular example, by the nick of time, thread B1. So P from thread B was able to saw semaphore value at that moment, which was 1, and was able to decrement this value to 0. Okay, and the thread B should return without blocking and will continue. But how about thread A? And thread A's P here lost, okay, and thread A will now see the semaphore count value being 0. And you cannot decrement this 0 value. So thread A has to block and wait until somebody increments this semaphore value to positive number, and then only then thread A will be able to decrement this semaphore value and be unblocked. Right. So thread A blocks and thread B will continue, and let's say at this moment thread B, again called P, it will see 0 and it should block. It is impossible for thread B at this moment to decrement. The thread B also needs to be scheduled out. So we have 2 blocked threads, and semaphore value is still 0. Still 0. All right, we need a third thread to unblock these 2 threads, one of these 2 threads. Let's say we have thread C, and thread C is the one that calls the increment operation called V. And let's say thread C about this time called V. And the result of V is it will increment the semaphore count value to 1. Okay. And also, the semaphore knows that there are 2 waiting threads. There are 2 threads, that's blocked on this semaphore. And semaphore will wake up either one or all threads. Obviously, at this point, you may ask, why all threads? It makes sense to wake up just one thread. You're right. Semaphore may take a look at how many threads are waiting and just pick one. But, in theory, you can wake up all the threads and let all the woken up threads to have a race. Again, just like at this point. Doesn't really matter. Only one will get it. So it doesn't really matter how many threads should be woken up. So let's imagine that the semaphore implementation internally wakes up all the threads, just like broadcast. And let's see what happens in that scenario. Okay. The both threads, thread A and thread B, they are still executing inside of this P operation. Okay. The P operation should return only when you are able to decrement semaphore count value. So they internally attempt to decrement the semaphore value again, okay, but the value is 1. And let's say in this case, thread A 1. Thread A was the one that was able to decrement this value to 0. And because thread was able to decrement, the thread A will return from previous P operation here, unblock. This means P finally returns. Okay. How about thread B? In this case, thread B lost, so it should be blocking here. like this. So the second P from thread B will not return because thread B was unable to decrement the semaphore the second round. Okay, like this. Let's say thread C at this moment called V again. Okay, increment the value, and this will change the semaphore count value to 1. And thread A was running, and now thread B was the only one that's blocked. So it will unblock because this will wake up this blocked thread, and thread B now decrements the semaphore count value from 1 to 0, and then the P returns. All right, so this is the operation of semaphore. You can use this behavior to synchronize multiple threads. All right, let's take an example from your textbook again. So this is semaphore BBQ. Blocking bounded queue, in this case, is implemented using semaphore instead of mutex and condition variable. And you have this over here, we have insert function and remove function. Interface behavior should be the same. And this is the implementation. All right, we're going to use the same underlying data structure. We have buffer and we have head and tail pointers. And these are the synchronization variables. We have 3 instances of semaphores. So the first one is mutex. Be careful. The name of this object is mutex. The type of this variable is a semaphore. It's still semaphore. Okay, we are not using the mutex lock here. So we just named it mutex because we are going to use it as if it's a mutex. Okay, and we supply this initial value to be 1. This is known as a binary semaphore. We're going to talk about it later. And we have 2 more semaphores. The first one is empty slots, and initial value is set to max, maximum number of empty slots in the beginning. And the last instance of semaphore is named full slots, and initial value is 0. So obviously, as the variable names suggest, these semaphore represents the number of available slots or number of unavailable slots. Okay. All right, let's take a look at the insert function. This area, this is our critical section. Okay, so we have mutex P and mutex V. So because this mutex, semaphore named mutex, is initialized with 1, essentially, by doing this, you can create a critical section. And if you look at the remove, we use the same mutex semaphore to protect this region, which is obviously the critical section of the remove function here. We can create this critical section by declaring a semaphore with 1 as the initial value. Okay, so only 1 will enter this critical section. Right. You may ask, how about waiting and signaling? Waiting and signaling is handled by these semaphores. So basically, before you do anything, you call this empty slots P, the P function, the decrement function of empty slots. And this P will block when the internal count value drops to 0. Okay, so when there is 0 empty slots, the insert function at this point should block. And then if it returns, that implies that you have available slot, and you perform this critical section, and then after exiting the critical section, you increment the full slots semaphore, okay, because you added 1 item. And there's a symmetry between insert and remove. And one thing that stands out with this semaphore BBQ implementation is that there's no retry loop. If you are comparing with condition variable implementation. The reason is semaphores, they remember, and the signaling, the P and V, they are exact. Okay, there's no such thing as a superior to wake up. And all the waiting logic is embedded with this number counting and waiting properties of semaphore. And you may say this looks better than the condition variable implementation because there's no retry loop. But I have to say this, if you're actually trying to solve non-trivial synchronization problems, the semaphores are really hard to deal with. Okay, in this particular example, you can cast this into this number counting problem very nicely, but not many problems fall into that category. So essentially, if you're using semaphores to solve synchronization problem, what you have to do is, whatever synchronization problem that you're trying to solve, you have to cast that problem into a number counting problem. That's a challenge. All right, binary semaphore. All right, so binary semaphore is a semaphore with initial value 1. We saw this just before. Okay, so this is the binary semaphore. Binary semaphore is not a special version of semaphore. It's a still semaphore. We named it such a way because the way we use a semaphore. Binary semaphore is defined as an instance of a semaphore that we intend to use as if it's a mutex lock. And you may ask at this point, okay, so is binary semaphore the same as mutex lock? In theory, they both provide mutual exclusion. They are used to create a critical section. So in theory, yes, but in practice, there are important subtleties. Okay, the binary semaphores are still semaphore. So that means the binary semaphore still follows the rule of semaphore. Okay, for example, can I lock it again while I'm holding the lock? So if you're using mutex lock, the answer is usually no, because even if it's held by yourself, you cannot lock it again. If you're using just a regular mutex lock, that is runtime error, or at least deadlock. But in case of binary semaphore, that's totally within the definition of semaphore. So the second time you call P, then it will block. So the compiler cannot complain, and the runtime system cannot detect that as an error because that's completely within the semaphore semantics. Another point here is, can I have someone else unlock it for me? For mutex lock, no, obviously not. Okay, if I entered a critical section by acquiring a mutex lock, then I should be the one that released the lock. So the idea of someone else unlocking the lock held by me is a nonsense. Okay, so in mutex lock, at least runtime check will raise alarm. Okay, but a binary semaphore case can happen. Okay, so it's completely within semaphore semantics. So if there's some kind of bug, somehow somebody else calls V, then that will essentially unlock the binary semaphore, and that's a significant problem